Welcome back to the interactive demo of how to come up with reasonable micro benchmarks. Now, as you can see here, I'm using the Godbolt or Compiler Explorer web tool, which I like very much using because it allows you to just play around with some source code and see what the compiler will output from it. So let's assume we want to implement a linear constant analysis, and for this we want to come up with some micro benchmarks. Okay, currently we have this empty main function here. Let's start with some integer variable and let's call it a. And as you can see now, this is compiled to this local instruction here. And this is actually the first case we want to handle in our linear constant analysis because we want to generate the data flow fact for %a from the 0 value. Alright, so this is already the first thing your linear constant analysis will have to be able to handle. And this will be your first test case. And now, let's assume our analysis is able to handle this very basic case here. Now let's assign it some constant value, and let's assign it 42. And as you can see, this assignment will reflect in this particular store statement here in LVM IR. So your analysis will have to be able to handle this store statement. So you're storing a constant value to an integer pointer. And actually, as in LVM IR, these registers here represent the variable with a pointer. You will always have this pointer indirection in here. Alright, now let's assume that your analysis is able to handle this, this storage here, right? Now we want to be able also not only to store some value, but we also want to be able to load this value. So let's define another variable b, and let's assign it the value of a. And actually now you see all of a sudden some more statements will be generated here. So let's decompose it. So first of all, we declare another variable b here, right? So this will end up in this further locus statement up here. But we are already able to handle a locus, so that's not an issue. Then we get those debug information calls here, but Phaser actually automatically ignores those for you, so you don't have to care for those in your analysis. Now what we see here is the load instruction, and the load instruction will load the value from A into this temporary here, and then again store this temporary to B. Now the new artifact or the new statement we see here is really this load statement. The store, assuming that we already handled it before, is also nothing new for you. Okay, actually it's a bit different because here we are storing a literal, and here we are storing a non-literal but a fact that we might get propagated to. But as A is constant here, this load will still propagate, or at least it should propagate, and then we store this constant value into B here. Alright, let's advance our example further. Let's say, and by the way, already the intermediate steps I'm taking here are all single test cases that you really should come up with, right? So I'm just interactively editing this file here to show what is possible. Alright, so now C and C++ allow you quite vastly to take some pointers. So let's see what happens if we declare a pointer variable and actually take the address of this value here. Now what you can see is that actually this results in a further store statement, but this time you're actually not storing an integer itself, like here, right? So this stores an i32, and this stores an i32 pointer, and this is somewhat a different case, because here you're really doing you're storing away a pointer, but still you want to propagate this %a to %b here. So yeah, your analysis will also have to be able to take care of this. All right. Now let's discuss some further cases. Now we have load and we have store. Let's discuss. Let's get some fields into play. So let's have a data structure here. So a struct A, and let's give it some field F and maybe some other field G. And now let's assume we have a variable of type A, and then we assign the field with 42. Actually, since we are in C here, so this is in C mode, we will have to type struct A here. Alright, and now it will compile. At least it should compile, or take some time. Actually, I missed this one here. Alright. Now you see we get this get element pointer instruction here. And now we are storing this constant integer here to %f. And now your analysis will have to take care of the aliases of %f. I think I am discussing this a little further in the slides at a bit later point, but at least you have another very basic example of what your analysis should be able to handle, and this will already involve quite some further development work so that you succeed in being able to handle this. And also, of course, you want to be able to load this value, and so let's go and let's load this value here, and your analysis should succeed in propagating this 42 here to x. Now the issue here is, of course, that if you want to be able to distinguish those fields, your analysis would have to be field sensitive. But even if it's not field sensitive, it should soundly propagate this here. Now, if we go and set the other field to, let's say, 13, then if your analysis is field sensitive, it should still reveal that x has the value 42 here. But if it is field insensitive, then both 42 and 13 will flow into A, and then we will over-approximate this. So those both fields would be merged basically together, and we would have to over-approximate it. In that case, we would get the bottom value here, so the most over-approximated value in the value domain letters. So either way, both if your analysis is field sensitive and if it's field insensitive, you should check whether this merging or the distinction is handled correctly, and this would be a test case that could do the very same. Alright, now let's go back to fundamental, so just not structure, just go back to an integer again, because now we are interested in some operations. So let's say we assign it again the value 42, and now we declare a different variable, and this will be, let's say first it is 2 times a, and let's make it a bit more beautiful. Always spaces around binary operators, please. So now you will see that this statement here is decomposed into the following statements. First of all, of course, again you have this alloca up here, which we don't take care of now. Then here the value that a holds is loaded here. And now we have this multiplication statement here, right? So this is the binary operator, and now yeah, you see that you multiply this operand here, %0, with the literal 2. And this is a linear expression, and as this is trivially constituted, so as this is a literal, you will still be able to propagate this in the edge domain, as the flow function for this is still distributive. So of course your analysis should be able to handle this properly. Now, mentioning distributive and distributive flow functions, of course we also want to check and make sure that in case we encounter something non-distributive, such as this expression here, that your analysis over approximates properly. So you could still get some flow functions here, but the edge function should take care of merging, not merging, but over approximating to bottom. So the binary statement responsible for not the binary statement, the binary expression for that, not the binary expression, the binary operand for that would be this add here, and you see both operands are non-constants or non-literals, and that is why we have a non-linear expression here. And this should also be reflected in your analysis so that it over approximates here. Alright, what else do we have? Well, we also have control flow structures such as if statements. And there, of course, also it should be made sure that merging is done properly. So let's introduce an if here, and now of course let's take some random value here, and then have one branch and then have the other branch, and declare the a before. Alright. And now let's don't assign something here, but assign something in here. Is 42. Alright. And now let's see what happens here. So we get this call here to the rand function, which we don't really look into at this point, and then we branch into those branches depending on whether the condition is true or not. And in one branch we store this 13 into A, and in the other branch we store this 42 here into A. And then the merge point would basically be this statement here, so we should make sure that the analysis reports bottom for A when we reach this statement here. So this again will have to be taken care of in the edge domain of your analysis. And actually there are more ways how this merge could occur. So there is a special instruction in LVM, which is the select instruction. And as you can see here, we don't have it generated in this statement here, right? So we might want to provoke be having this statement generated. And with growing experience in LVM IR, you will also get some experience what to write or what you will have to write in source code in order to get some particular construct in LVM-IR. So for this select statement, there are two tricks we can take. The first one is actually to increase the optimization level a bit. So far I've been using optimization level 0, which optimizes nothing. And now when I go to 1, we will see that everything is actually optimized away. Except for this function call here, because this might have side effects the compiler is not aware of. But of course we want to have the effect for A, so the propagations here for A to be effective. So let us return A then, and then of course we have to change the signature of the main function, and then you see the select instruction here, right? So depending on this condition here, we'll either take this value or it will take this value, and a reasonable integer constant propagation analysis should also be able to handle this case here as well. Actually, there's also a different way to provoke this select instruction being generated. You could use the ternary operator, which of course in a way is a bit discouraged for production use, because it just makes the code a little hard to read, or it can make the code a little hard to read, but for our purposes here we can just use the ternary operator, and by doing so we will provoke that the select instruction is being generated also when we have optimization level 0, right? So here we see the select statement being used. One aspect to keep in mind is that your micro benchmarks should really test conceptual abilities of your analysis and not necessarily some source code constructs. For example, in this code here, you might think maybe that testing loops and stuff is a good idea, and in some cases it does really, but not in this one here, because what is the conceptual concept we would test here? In the end, we would only test that merging 13 and 42 is over approximated, so yields the bottom element. Why is that so? Because we have one branch that skips over the loop here entirely, and then one branch that goes into the loop. Now, if we expressed this here as a do-while loop, then again we are not really adding value here, right? Because here we have this 13 set, and then we in any case will enter this branch here and then possibly propagate through it over and over again. So here at the first time we kill the 13, and at the following times we just we kill the 42 over again. So there is no real merging taking place, just killing values. So this is not really adding any conceptual value here. But on the other hand, what is adding some conceptual value is actually if we, for example, not only test that merging two distinct values will lead to over approximation, but also to test that assigning or merging to identical constant values still leads to no over approximation actually by trying something like this here, right? So here now we get the select statement, and now both operands of the select statements are the 42, and the expected result for this would really be that we do not over approximate here, but still know that A is 42. And now, having handled this in a select statement, of course, also we want to be able to handle it in an if, because this is conceptually different from the select statement, as now we have some branching here. So actually, let me fix the syntax a bit. So A is 42, and then else A is 42 again. Like this. It's a little ugly written, but I think you get the point. So here, of course, we don't want an over approximation of A at this merge point here. And this is conceptually different because we indeed have multiple basic blocks here, and we do have control flow edges going from here to here and from here to here, and yeah, there's a difference compared to what we have with the select statement. So as you can see, like your analysis, also your micro benchmarks will grow and grow in complexity, and you will have to keep in mind multiple layers of concepts. So you will have to take into account control flow, you will have to take into account the kind of statements, the kind of data flow facts, the multiple cases of how you want to handle the statements, and also the flow facts. You have to take care for your edge functions, and you have to understand the intermediate representation of your source code that is being analyzed. And of course, with all of that, you will get better and better over time. And the best way to get better at this is obviously just start doing it. And yeah, this is what I would like you to encourage. Phaser is freely available, and you already have worked with it a bit, hopefully, in the labs. But I still encourage you to work more with it. It is actually a lot of fun, and yeah, I enjoy it very much. And with that, I would like to conclude the practical demo of the micro benchmarks.